Okay, so let's do the beam demand now. So if we go back and look at this problem, so we're going to hang on and save share for a little bit. We're on demand of the beam. Okay, oops, sorry. We're on demand of the beam, this guy, and then we'll do the adjusted bending stress capacity of the beam. So this one will cover demand. All right, so let's look at this interior beam here. And it's a 6x12 hem-fur number 1. So now we're looking at number 1 grade beam. It's 12 foot long, and we've got to figure out the load on this beam. And there's a couple ways to do it, but essentially it's going to be all the stuff here, right? All the tributary area here. You can go ahead and add up the self weights of all the joists that are the half joist this way, half joist that way. You can add up the live load. You can add up all the PSF from the floor weight, all that good stuff. Or what's really happening here is that the joists are being framed straight into this beam. And so I actually think that the better way to think about this for the load path is to take the reactions from the joists. Right, and this middle one will have will have a reaction on both sides, and then apply it to the beam, add the beam self weight. So we've already done the calculations for the joists, and so we just need to figure out what these reactions are, which is pretty straightforward. Figure out how many there are and put them all on the beam. One of the things that if you don't have any other information about the number of joists is to just assume that the first one's spaced halfway to the edge. So really over here. And then the last one is also spaced halfway. So you end up, if you just divide 12 feet by 16 inches on center, usually you'd say, oh, that's the number of spaces, but because we start a halfway from the exterior, that'll actually be the number of joists. Okay, so let's just go ahead and write this down. So beam demand, if I look at that half spacing, so I'm just going to write this briefly here so that you have it for your notes. So if I've got my beam here and I've got joists on both sides, so the distance here, right, and da 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 da, and then we have a half distance to the first joist here, and on and on. So we've got a half space, and then these guys are spaced at S, so this is half S, S equals 16-inch OC on center. All right, and this is a 12-foot beam. So first, 12 feet divided by 16 inches on center is going to give me 9 joists. Okay. If you know and you've got a plan that's laid out that has one that starts at S, you adjust accordingly, right? This is just a basic math problem. All right, so what's the joist load? So if I'm going to take in the reaction on each side of these things, if I take one joist, it never hurts to draw these things out, particularly the first time. If I had one joist, if I look back in my notes, I came up with dead plus live of 70 pounds per linear foot. This is a 10-foot joist. And so I just need that reaction. And for the other one, I need the other reaction. That's going to be 71 times 10 over 2. So WL over 2. So 710 over 2. And then I have 2 of them, so I'm going to end up with 710. Right? So I'll just write this out kind of in detail. So 710 pounds over 2 is one reaction, but I've got 2 of those reactions. Write whatever you need there to be able to interpret this when you go back. 9 joists, and that's going to be a total of 6,390 pounds total load on this beam. Okay, that's just a sum of pounds. You got to watch units here so you don't get yourself confused. Now, what does that really look like on the beam? Okay, well, it's going to be the 9 joists across here. So this is not actually uniform. There's going to be 6,390 divided by 9 of these things. on each. However, we can assume for design, it's fine to, usually we don't like you smearing stuff into a uniform load, but these are uniformly loaded across the beam at 16" on center. Okay here to say this is about equal to a uniform load. Okay, so that uniform load would be 6,390 pounds per, it's a 12-foot long beam per 12 feet, which is equal to 532.5 pounds per linear foot. Okay, if you want to do it the other way, where you add up all those loads again, once I've put all the loads together, I don't want to go back and divvy them all back out again. So this is how I would do it. Plus, this follows the load path. But if you do it a different way and get to that, that's fine, or something very close to that. All right, the dead load of the beam itself, or self-weight of the beam itself. In your book, they tend to just call it dead load, not self-weight, which is fine. I'm just used to teaching pre-stress where I try to keep those separate. Also, because if I go back and I change beam, I know exactly which part's the self-weight. But either way, it's all the same. It's a 6x12. It's the density is the same as before. It's the same type of wood, which was 29 something. Sorry, 29 something. It was about 30 pounds per cubic foot. If I go into table 1B of the supplement, this is repetitive of what we've done before, so I'm just going to breeze through this. Of the supplement, I get 13.18 pounds per linear foot of weight of the beam. So now my actual total uniform load is the 532.5 plus the 13.18, and we round to the nearest pound, and we get 546 pounds per linear foot. So you work through, make sure you can get 546 pounds per linear foot no matter which way you're doing this. Okay, so now we've got the load that goes into the demand, right? So now we just need to find the moment. Since we're working on flexure, moment equals WL squared over 8. In our case, we've got 546 pounds per linear foot. You use your unit crossouts and all that however you see fit. You'll see I'm somewhat lazy on my units once I've got a pattern down, but the first time I do something, I make sure that my units are going to cross out correctly. So this is 12 foot square, or no, pounds, yeah, 12 squared over 8. Everything's in feet there, so this is 98.28 pound-feet. So little f sub b is going to be moment over the section modulus. I get this guy from table 1b as well. And this is the major axis xx s sub xx direction. So I'm going to get a moment of 98.28 pound-feet over, if I look that up, I get 121.17 inches. Oh, sorry, no, 121.2. Oops. Hang on here. Should be 121. 121. Sorry, my headset's being weird. 121.2 inches cubed. Now I need to get my units, inches per foot, correct here. And so I will get 973 psi. This is F sub B, so this is our demand in bending. Okay, so cut this video off and we'll move on into the required bending stress, in other words, the adjusted allowable bending stress.